Hi. So in the last video we looked at, we discussed some of the vocabulary surrounding waves, specifically periodic waves. We defined the amplitude of the wave to be the maximum displacement of any individual piece of our medium. We defined the wavelength of a wave to be the length of one cycle of the wave, maybe as it travels to the right or left or up or down. We describe the period of a wave to be the time it took for one cycle to pass some specific point. And then the frequency is 1 over the period. So what I want to do now is I want to come up with an expression for the speed of the wave and relate that to the wave's wavelength and its period. And again, I want to point out here, which maybe I didn't highlight quite well enough in the last video, that this wavelength, we're representing it with a lambda, and that's really small in the figure. So lambda is our wavelength. That's the symbol we're going to use for that. All right, so let's see about figuring out expression for velocity. All right, so what we have here is basically a set of snapshots. We can picture there at time t equals 0 seconds that our person is going to start oscillating a piece of string up and down. So they're going to jerk it upwards and then back down and then down a little further and then back up to where their hand started from. So what they have done there is they've taken their hand through a full cycle of motion. Okay, this is going to create a wave. That wave is going to start traveling to the right. Okay, well, let's see how. Let's see here. How far does our wave, our starting bit of our wave travel in one cycle? Well, the distance traveled there by the starting bit of our wave, the distance traveled by our wave front in one cycle is lambda. Doing the best job I can, guys. Sorry, that's lambda. All right. Well, how much time was the wave moving as that wave traveled? Well, we can see there that the time is the time for one cycle. Okay, so time. What's the time for one cycle? It's the period. And then I'll remind you that, well, that speed is distance over time. So we can say here that our speed of our wave is wavelength divided by period. And there in the last slide, we saw that frequency is 1 over the period. So we could substitute that into our expression for velocity. So we could substitute that in here, right here. And we could get out the equation that, well, not only is velocity equal to wavelength over time, velocity is equal to wavelength times frequency. Okay, and that ends up typically being the most useful form for the equation for the speed of a wave. And this equation is always true for periodic waves. It doesn't matter if it's a wave on a string, if it's a water wave, if it's a wave on a slinky, if it's a sound wave, if it's light. This equation is always true for periodic waves, that speed is equal to wavelength times frequency. So this is a general expression. All right, let's take that and do something with it here real quick. Let's see here, 1 second. Let's take this and do something with it here real quick. Let's look at this example problem. We're going to analyze AM and FM radio waves. So AM and FM radio waves, these are just electromagnetic waves. It's kind of weird to think of radio waves as being light waves, but that's basically what they are. You know, when we say the word light, we think of what? Visible light, but really light is all the way across the spectrum of electromagnetic waves. This could be ultraviolet, visible light, infrared, X-rays, gamma rays, microwaves, radio waves. These are just basically different frequencies of light. So if we've got AM and FM radio waves, that means that they are going to travel at the speed of light. If you did not know, the speed of light is 3 times 10 to the 8th meters per second. And it says that the AM radio wave has a frequency of 1,230 times 10 to the 3rd hertz. The FM wave that we're going to analyze has a frequency of 91.9 times 10 to the 6th hertz. So this is a little interesting, a little bit of an aside here, but when you tune your radio, your car radio, on the AM band to 1230 AM, you're actually tuning it to the frequency of a carrier wave. And the frequency of that carrier wave is 1230 times 10 to the 3rd hertz. So that number there matches up with the, at least the first 4 digits of the frequency of the wave you're tuning into. And we'll leave it at that. Same deal with the FM wave now, except now instead of times 10 to the 3rd hertz, we've got times 10 to the 6th hertz. All right. What's the problem asked for? It asks for the distance between adjacent crests. Well, the distance between adjacent crests, there we go, there's our periodic wave. The distance between adjacent crests would be right there. What's the distance between adjacent crests? That is the wavelength. So that's what the question's asking for, is what's the wavelength for these 2 waves? All right, well, given our speed of a wave on a string equation, or speed of our, not on a string, our speed of a wave equation, our equation V is equal to lambda F, this problem's simple. We just need to rearrange the equation. And what we see here when we plug in our values that we're given is that the wavelength for this AM radio wave is 244 meters. The wavelength for the FM radio wave is 3.26 meters. Okay. It's these differences in wavelengths that explain some of the different behaviors that we see in FM and AM radio waves. So you can actually pick up AM waves, AM radio station from much further away than you can pick up an FM radio station. If you've got if you're listening to radio at night, where they're able to turn the power up on the radio, the broadcasting antenna a little bit, you can actually get an AM station from hundreds and hundreds of miles away. So 800 miles, something like that. I'm here in Radford, Virginia, and I can pick up a radio station from Cincinnati. Yeah, I know that for sure because I've listened to it on my car radio. Could we pick up an FM station from Cincinnati? No, we could not. Why is that? It's because that much smaller wavelength scatters much more easily. This signal attenuates, and so we don't pick up that signal. This difference in wavelengths also explains a little bit about, well, it actually explains exactly, although I'm not going to delve into it, about why we can pick up an FM signal a little longer as we travel through a tunnel than we can an AM signal. It's due to the differences in the wavelength sizes. All right, so let's see here. What's next? Next example problem we're going to do is one for a record. We think about a record. There's a needle that sits in the grooves of the records. What happens? Well, basically this record moves underneath the needle. So we can picture it as the record moving underneath the needle, or we can picture it as, from the perspective of the record, the needle moving across the top of the record. At any rate, the thing that actually causes the sound that a record generates is little individual grooves, wiggles in the grooves in the record. So this particular record is the most boring record of all time. It has just a steady frequency of 5 kilohertz cut into it. That's 5,000 hertz, something like really annoying, right? But at any rate, that's the sound that comes from this record. So it's a 5,000 hertz frequency. And what we want to figure out is, well, let's see, what's the wavelength of this groove? What's the what's the distance there for individual cycles for our groove that actually would produce this 5,000 hertz tone as the needle travels across the top of this record. Okay. All right, so that's our goal. Let's see what we can figure out here. Well, we're given the frequency. The frequency is 5,000 hertz. And what do we want to figure out? We want to figure out the wavelength. And we can probably guess that we are going to use our V is equal to lambda F equation. That means that, let's see, if we rearrange that for lambda, lambda is going to be equal to V over F. Well, that's great. We've got F. What about V here? V would be the speed of our needle relative to the record. What are we given? Well, we're not, and let's see, the units for V there, what would they be? Meters per second, right? That's the units for speed is meters per second. But we're given something here, but we're not given our something in meters per second. Instead, we're given our something in radians per second. So if we can reflect back on physics that we learned in the past and think about what that radians per second would be, well, our record is, what is it doing? It's rotating around in a circle. That radians per second describes the angular speed of our record. Our angular speed of our record is 3.49 radians per second. Great. How do we translate that into a linear speed? How do we get V out of that? Well, we might recall that V is equal to, our linear speed is equal to angular speed times radius. Well, what's our radius? Well, it's there in the picture. That's where our needle is. That's how far away our needle is from the center of the record. It's 0.1 meters. So let's see, let's do the math here. 3.49 radians per second times 0.1 meters for radius gives me 0.349 meters per second. Okay, I can then plug that into this equation up here, 0.349 meters per second, divided by my frequency of 5,000 hertz. And when I do this, I get a wavelength of about 7.0 times 10 to the -5 meters. Okay, so there we go. So on this world's most boring record, I would see grooves that are 7 times 10 to the -5 meters long before they repeat themselves. So I could put the record underneath a microscope and I might see little individual grooves that repeat themselves every 7 times 10 to the -5 meters. Kind of cool. This is actually how we get sound from a record. Of course, the sound then propagates through the air, but that's a topic for another lecture. All right. That does it for this one.